Today we want to talk about inverse functions, specifically in the context of calculus, finding the derivatives of inverse functions. This is going to give us derivatives of natural log, also of inverse sine and inverse tangent. Those are going to be the three that are going to be important to us moving forward. I don't know if important is exactly the right word, but we're going to pretend that it's going to be important to us moving forward. So the three that we want to acquire today: the derivative of natural log, the derivative of arc sine or inverse sine, and the derivative of arc tangent or inverse tangent or tangent inverse. We're going to start by just writing down what we're aiming for. The derivative of natural log of x is 1 over x. Natural log of x is the log base e of x. So this is natural log or log base e. This is one that we need to know. The derivative of natural log of x is 1 over x. The derivative of arctangent is 1 over 1 plus x squared. Arctangent is the inverse tangent. Arctangent is the inverse tangent function. Sometimes we write tangent, the inverse tangent as tangent inverse of x. We don't say tangent to the minus 1 of x, we say inverse tangent of x. Unfortunately, we put the part that says inverse after we read the part that says tangent. We just can't read this symbol in order. Although I will read it in order a lot, because I'll forget that I'm supposed to say inverse tangent. I'll say tangent, say shit, I need to say inverse, and I'll just say tangent inverse, because that's how it's spelled. But when we see that symbol, we're going to say inverse tangent. The other way you could write it is with ARC in front of it and say arctangent. And that will mean inverse tangent. We have to notice the notation arctangent because we don't really like duplicating our notation. But to the minus 1, that just means inverse function. That's one of the instances where in math we start reusing some notation. And then kind of cross our fingers and hope it doesn't cause too much confusion. Another one that we need to know, the derivative of arc sine is 1 over the square roots of 1 minus x squared. Arc sine or inverse sine . So we'll pronounce that as inverse sine. And similarly, we might write this as sine to the minus 1 of x. We're only writing sine to the minus 1 of x. We mean inverse sine. We mean this as an inverse function. We have a different word for the reciprocal of sine. We call that cosecant. So if I wanted sine to be raised to the negative 1 power, I'd write cosecant. But with arctangent, you can pronounce that as arctangent. I just gotta put a pronunciation guide underneath. Just say arc and then tangent. Don't say arctan because now you're just reading the abrev, and we don't do that. Here's where we're headed. The derivative of natural log of x is 1 over x. The derivative of arctangent of x is 1 over 1 plus x squared. The derivative of arc sine x is 1 over the square root of 1 minus x squared. One of the interesting things that's going on here is that we're taking the derivative of a transcendental function and we're getting an algebraic function. So that's kind of neat. Not really relevant to us at the moment. That's just kind of an interesting observation. DVD bonus material, gonna end up on the cutting room floor. But that's one of the things that's interesting about these three derivatives. These are three new basic derivatives that we can use in combination with others. So this is three new basic derivatives. So we have three new basic derivatives that we can use in combination with other derivatives. Or sorry, with our rules for combinations of derivatives. So for example, if I had a function, let's say y is equal to x to the third arc sine of x. Arc sine is one of our new basic derivatives. You've seen it written down one time, so now you will remember it forever, because I mean, that's how human memory works. You just need to see things one time, and then you remember it forever, and you're perfectly proficient, right? Isn't that how, that's how it works, right? That's why we have prerequisites, where the second class ends exactly where the, starts with exactly where the first class ends. So when we're looking at this, we have to decide, we see an x cubed, we see an arc sine of x, we have to decide how they're combined. I see x appears twice. So I see two things happening to an x cubed and an arc sine x. I see those two different things happening to x, and how are they combined? They are combined with multiplication, so we're going to use a product rule. I'm going to list as my first function x cubed. And so the derivative of the first is 3x squared. And my second function will be arc sine, our shiny new one. And so the derivative of the second is 1 over the square root of 1 minus x squared. Now we can put together in the product rule. We take the derivative of the first times the second. Plus the first times the derivative of the second. Since the derivative of the second is a fraction with a 1 for a numerator, I'm just going to take the derivative of the, take the first and stick it up on top. It's just a new basic derivative that we're going to see come into rotation. So we just have to be prepared for it. We have to know this one. The derivative of arc sine is 1 over the square root of 1 minus x squared. Because the derivative is a 1 over 1 minus x squared, it does look a little bit weird if I start putting making compositions with arc sine and arc tangent. So for example, if I take the x cubed and put it in the inside the arc sine. So if I have, say, y is equal to arc sine x cubed. Now I see the biggest clue that we have here is that there's going to be a chain rule, and only a chain rule, is that the x only appears one time. We see multiple things happening to the x, but we only see one instance of the variable x. So we're not seeing functions of x being multiplied together. We see the first thing that happens to the x is the x gets cubed. And then the second thing that happens to the x is we do an arc sine of whatever the result is. So this is going to tell us a chain rule because the x only appears one time, but we see multiple things happening to the x. So our read on this one, I don't do this all the time, but our read, the first thing that happens to the x is x gets raised to the third power. And then the second thing that happens to the x is that we do an arc sine. That tells us that the inside function is the x cubed and the outside function is the sine inverse, or the inverse sine. See, I'm already doing it. The outside function is inverse sine. And that's going to tell us how to proceed. So our inside function is x cubed, and our outside function is inverse sine of stuff. So when we go to take the derivative, we take the derivative of sine inverse with respect to x cubed. So sine inverse, it looks like 1 over the square roots of 1 minus thing squared. The derivative of sine inverse of thing is 1 over the square roots. Separate it out, fix it later. 1 over the square root of 1 minus thing squared. In this case, thing is x cubed. Then we multiply by the derivative of the inside, 3x squared. A lot of times when we first start doing derivatives, where our derivatives have these squared bits in them, we don't like it. We do not like this. It's just something that we have to get used to. Here we have all the details. And then of course we'd want to simplify this. I've got an x cubed squared. That needs to be turned into an x to the 6th. And I got a 3x squared with a numerator of 1. So I'm just going to put all that together and put the 3x squared into the numerator. And this will be the square root of 1 minus x to the 6th. Just taking the chain rule and using it, the chain rule and our new basic derivative. How's everybody okay? Everybody looks so stoked that we have inverse functions. That's all. Fuck yeah, inverse functions. I think this is fine. We have a new basic derivative. The derivative of natural log of something is 1 over that thing times the derivative of that thing with the chain rule. This is once again a chain rule because I only see the x one time, and there are 2 things happening to it. Number 1, we do a cosine. Number 2, we natural log. So there are 2 things that we can see reading this problem. So our read on this problem first thing that we did is a cosine, and the second thing that we did is a natural log. So that tells us that the inside part is the cosine, and the outside part is natural log. So inside is our cosine. And our outside is natural log. So our derivative is going to be the derivative of the outside with respect to the inside. In this case, the derivative of the outside is 1 over. The derivative of natural log of stuff is 1 over that stuff. Times the derivative of the stuff. The derivative of cosine is negative sine. Wouldn't want to leave it like this. This seems a mess, so we might want to write this as negative sine over cosine. But we have another word for negative sine over cosine. What's another word for sine over cosine? Tangents. So the derivative of the natural log of cosine is negative tangent x. Important to notice these things because eventually we are going to be doing this process backwards. Because every time you learn something in math class, you have to learn it forwards and backwards. Oftentimes, quite literally forwards and backwards. If I reverse the natural log and the cosine, I get a different looking function. So I'll give it a different name. So if I have the cosine of the natural log of x, now I've switched the roles of natural log and cosine in the order. So our inside is natural log of x, and the outside function is cosine. So whereas in the previous example, we're taking the derivative of natural log of something, in this example, we're taking the derivative of cosine of something. So the derivative of cosine of something is negative sine of that thing times the derivative of that thing. In this case, that thing is natural log of x. And the derivative of natural log of x is 1 over x. One of my factors is just a numerator of 1, so let's take the other factor and put it on top. But I always leave my negatives out in front of my fractions. I don't like the look when the negative is clearly up on the top of the fraction. I don't know why. It's not incorrect. I won't mark off points, but I want you to know if you write your negatives on top of your fractions, I'm not taking off points, but when I look at your answer, I go, yeah. That's kind of, yeah. If you put the negative in the denominator, it's not incorrect, but I will be angry. I was like, oh man, ugh. It's like a more visceral reaction when I see that, right? So like, it's a different, like, there's no difference between these fractions, -2/3. And I'm like, oh, yes, that is how we write a negative fraction. That like, that's, I don't know why I look at this and think that's okay. And then when I look at -2/3, I'm like, oh, ugh. That's kind of, yeah, that looks bad to me. I don't know if you had an opinion on this. I don't know if this just made you have an opinion on this. Some of you are like, oh, don't care, never cared, still don't care. Some of you are like, oh, now I'm starting to care. Damn it, Leach, why did you have to do this? Well, that's because. But if you do, so this is kind of ew. But if you're like, oh, 2/-3, okay, I know it's the same thing, but ew, no. Ew, no. That's like a higher level of ew, right? So this is ew, no. And I don't know why. I don't know why. I don't know why this first one, I'm like, oh, yeah. These two equivalent fractions, I don't know why I'm like, oh, no. Because it doesn't matter. They're all the same. Once again, I wouldn't take off, except if I plug this in on Canvas, I'm writing the first one because it all has to go in one line anyway. And if you write 2/-3, I'm not putting that in for you. I guess I am discriminating. ACLU. So from a single line syntax standpoint, like -2/3, that's like these first two are just like that. And it's like, aha, I can't tell. But if you write 2/-3, Canvas is going to be like, oh, no. Once Canvas starts saying no, you can't change its mind. Any questions? Comments? Slide remark? I don't know if it's because I have to write a lot of math that I don't care about like looseness and variability in like spoken language, or if it's in spite of that. Let me explain what I mean. Literally means emphasis now. I don't care what it used to mean. If you are literally dying, that just means you are dying. You're not literally dying. It's just used for emphasis. It's okay when something is very funny, and if you're laughing and rolling on the floor laughing, you can say, I am literally dying. That is grammatically correct. This is a hill that I will fight from. I'm not going to die on it because I'm going to fucking win, because that's how language works. So you don't, if you're like, that's not what literally means. It does now, in this context, it does. Get over it. I've had to give up some of my favorites, like begging the question. Begging the question means raising the question now. It didn't used to. It didn't used to. It was arguing, assuming your conclusion to make your argument. It's kind of circular reasoning. That was begging the question. But now people, I guess people thought it sounded cooler to say begging the question than it did to say raising the question. So when they meant raising the question, they started saying begging the question. Now, guess what? Begging the question just means raising the question, because that's how language works. So I don't know if I accept that because I write a lot of math, or in spite of the fact that I write a lot of math. And that bothers me sometimes. Then eventually I just come to the conclusion, I don't think anybody really gives a shit what I think, so I let it go. How's everybody okay? I cannot come into contact with the table on which the camera sits without, it's like, touch gently, I'll put this down gently. And it's still like, if I'm Blair Witching some of you, because I like bump the table and the whole thing's like, whoa, sorry. So we have learned, or we're starting to learn, we're just starting to add to our basic derivatives. We've got 3 more basic derivatives. I do want to talk a little bit about inverse functions and how inverse functions work, just as a quick reminder. So let f of x be a function. The inverse of f our notation for f inverse was to write f inverse. Doesn't work when you're speaking it. F to the -1. But we don't read f to the -1 as the reciprocal of f. We read it as the inverse of f. So when you see f to the -1 of x, we're going to read that as f inverse. It's in quotes because that's how you speak that symbol. The inverse of f denoted f inverse of x is a function. It inverts what the function does. It gets you back to where you started. If you apply f of x to a function, the inverse will take you back. Has to work the other way too. F of f inverse of x is equal to x. The inverse undoes whatever the function does. Gets you back to the start. The inverse undoes what the function does. The inverse undoes what the function does. I can capitalize, that's a whole sentence. If our function is just subtract 5, our inverse is add 5. Because if I subtract 5, then add 5, back to x. If I add 5, then subtract 5, back to x. One of the things that complicates matters a little bit is that a lot of times we have like 2x minus 5. We want to make sure that we do inverse operations in reverse order. So this is just a collection of operations. 2x minus 5 says first multiply by 2, then subtract 5. If we want to write the inverse, first we will add 5, then we'll divide by 2. We perform inverse operations in reverse order. First we'll add 5, then we'll divide by 2. We look at what g of x says to do. G of x says first multiply by 2, and second subtract 5. So if we want to undo that, we have to perform inverse operations in reverse order. We have to go back to where we started. So first we'll add 5, x plus 5, and second we'll divide by 2. We do not want to have to write down the order of operations for every function. This is something that is happening in the background. This is how we read and conceptualize what the function is telling us to do. So if I trade the order of operations of multiplying by 2 and subtracting 5, then the function would look like this. 2 times the difference between a number and 5. So the order of operations in this example, first, capital G says first subtract 5 and then multiply by 2. So to undo that, the inverse will first divide by 2 and second add 5. So our inverse will take x and first we'll divide by 2 and then we'll add 5. Now, because we've been through algebra and this function is so small, we might look at 2 times the difference between x and 5 and just rewrite this as the difference between 2 times x and 10. Just rewrite it as 2x minus 10, in which case our inverse, we might rewrite 2x minus 2 times the difference of x and 5 as 2x minus 10, in which case the inverse will be, here we are multiplying by 2, then subtracting 10. So subtract 10, then divide by 2. But this is the same. X divided by 2 is x over 2. Negative 10 divided by 2 is 5. So there's no difference. I'm not telling you something new. This is what you learned before when you wanted to find the inverse of a function. I'm reading it slightly differently. That's the difference. Questions? Other things that we need to know. So the reason that these were all very simple is that the domain and range of all 3 of these functions is all real numbers in both directions. When we make an inverse function, the domain and range switch. The domain of a function is the range of its inverse. The range of a function is the domain of its inverse. So for example, if we have a function, let's say e to the x, the inverse of e to the x is natural log of x. E to the x and the natural log of x are inverses of each other. Natural log of x is the exponent, is the power of e that's equal to x. So if I write e to the natural log of x, that's just x, and the natural log of e to the x is x. The domain of e to the x is all real numbers. And the range of e to the x is non-negative numbers. So starting at 0, but not including 0, and going to infinity. This is interval notation. I just have the left endpoint and the right endpoint. There's no right endpoint, so I just put infinity. So this here is the set of all real numbers that are strictly greater than 0. 0 is not included. We can't raise e to some power and come up with 0. And what this means for the natural log is that the domain of natural log is the range of the function of e to the x. And since the domain of e to the x is all real numbers, the range of natural log of x is all real numbers. Here I have graphed in red the e to the x function, and then in blue is the natural log of x function. Another important thing to note is that the graphs of the inverses will be reflections about the line y equals x. Any questions? How's everybody okay? It's like, oh yeah, we totally remember our inverse function stuff. One thing to remember is that not all functions have an inverse. Not all functions have an inverse. Another way to say this is not all functions are invertible. Not all functions are invertible. Not all functions have an inverse, but sometimes we can get kind of an inverse if we restrict our domains and ranges. We restrict the domains and ranges of our function, and then we can build an inverse function. So not all functions have an inverse, but sometimes we build them anyway. You can see I'm struggling to not go on to a third page because I already wrote 1 out of 2 on the first page. And there'd only be like 1 line on the third page. And even though it's a reusable notebook, I don't want to flip pages. So I'm cramming everything down. So not all functions have an inverse, but sometimes we build them anyway. So you can see how close, there's the QR code. So for example, x squared is not invertible. Because if I say we landed at 4, you don't know whether we came from -2 or +2. You don't know where the 4 came from. So we can kind of build a pseudo inverse. We can either use positive square root of x by restricting the domain of our original function, or we can go with negative square root of x. Depending on how we restrict the domain. Any questions? How's everybody okay? Not too much for a Wednesday? Is that even a lot? I don't even know. Hard to tell. I'm just saying that y'all are hard to read. That's all I'm saying. It's hard to read what's going on. So I'm like, oh, let's do the group activity. And to me, this feels like super awkward, but I don't know if y'all are feeling awkward. You seem to work well together. That's just based on on observation. I'm like, oh, here are some inverse functions. And I look out and it's like, oh, it looks like you all are remembering. But remember, me personally, I am remembering about inverse functions, but I'm remembering everything that I know about inverse functions, which goes back twice as long as most of you's been alive. And I don't know if I can accurately recall what it was like to learn about inverse functions back whenever it was I first learned about inverse functions. You know what I mean? I can make some inferences about this. I said this happened in algebra, but intermediate algebra, and it was elementary algebra that I had all the trauma from. That's what I hated, elementary algebra. By the time I got to intermediate algebra, I was kind of okay with this. But once again, that's only memories. Memories aren't recordings. They're just impressions of things that we've had in the past. Do you know what I mean? Memory just doesn't work like a recording device. The stuff that you think you remember, you don't actually remember. You don't have a recording of it. You probably made a lot of that up. You know what I mean? I mean, it's different now, because there's a lot more recordings of y'all when you were younger than there are of me when I was younger. Because it was a pain in the ass to make recordings of video images when I was a kid. You had to get some guy with a stone tablet, and he would carve one picture, then he would grab another stone tablet and carve it. You had to go really fast. Eventually, we started using like these little birds and put them in a box. And every time you open the side of the box, the bird would look at the camera and shrug and say, "It's a living," right? That's a Flintstones reference, which is even older than I am. So I don't know who the fuck is supposed to get that one, but there it is. Anyway, inverse function. That's going to do it for today. I will see you all on tomorrow. Remember, tomorrow is the last day of class for this week. 4-day weekend, no Friday, no Monday. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. Somewhere there's a sign-in sheet.
There's no class Friday.
No class Friday.
Yeah.
What a nice surprise.
Right, yeah.
Or Monday.